In this video, we're just going to revisit the fourth problem in the in-class problem set that was posted on on Blackboard. And what I'm going to do is I'm going to first let's just kind of revisit the notions and the ideas that are behind the Newton's Raphson's algorithm when finding the square root of a number. Okay, so the algorithm, the way it works is um, let me just put down this equation here. So it says the new approximation or the new value that you get back from this algorithm. Let's denote that with I subscript of a subscript of I plus 1, and this is equal to the previous value that you had, the previous approximation that you had, ai, and n is referring to the number that you're trying to find the square root of, and again ai is your previous value, the previous solution that you had for the square root of n, and this is divided by 2. Okay, so the way this works is this n over here refers to the number that you want to find the square root of, and AI is basically the previous approximation, the previous solution that you had, which was the square root, which was the square root of that n. And now with this new iteration that you've just done, this is the newer approximation, a slightly better version of the square root of n that you currently have. Okay, so this is on iteration, let's say I plus 1. Okay, this was at iteration I, and so forth. So you keep on applying this, keep on applying it over and over again. And the idea is that if this were to converge, so meaning if you start with some really initial approximation that was a0, which was the square root of n, okay, you start with some initial value a0, and let's put that initial value in the box there. And as this algorithm moves on and on and on, meaning you get a of 1, you get a of 2, a of 3, so at some point you get a of n, and then you get a of n plus 1. The idea is that at some point, these values that you keep on getting will become very close to each other, meaning they are converging. They're converging to some kind of a true value. So, which means that the difference of an plus 1 minus an should kind of approach to 0. Okay, they should become very close to 0. In other words, if this is going to be equal to 0, then your newer iteration to get back a of n plus 1 should be equal to a of n. Okay, because these values become very close to each other, meaning in theory they should be completely equal to each other. Okay, now what I'm saying here is, if this were to happen, and revisiting this equation here, if if a subscript n plus 1 becomes equal to a of n, meaning this value a of I plus 1 is completely equal to a of I after many iterations. So this could be rewritten as a equals to a plus n divided by a over 2, and then if I just take 2 on my other side over here, that becomes 2a equals to a plus n over a. And just doing basic arrangements of these variables here, I can get 2a minus a, that is a, and then bring that a on the other side, that becomes a times a equals to n. So I've got a square equals to n, or I've got a equals to square root of n. So this tells you, the Newton's Raphson's algorithm tells you that this a at some point will be equal to the square root of n. So that's kind of the basic theory. That's kind of the basic some of the notions behind the algorithm. And what we're going to do is we're going to use this algorithm to implement this in Haskell. Okay. Now again, let me just clean this up a little bit over here. And what I'm going to do now is I'm just going to let's just think about given some initial value, given some initial AI. Okay, how do I go from AI? How do I go from AI to a newer solution, a newer approximation? Meaning, how do I go from AI to AI plus 1? Okay, this is pretty straightforward. I've already given you the equation. The equation here is, in order to get this AI plus 1 is simply equal to AI plus n of AI divided by 2. All right, why don't we make an equation? Why don't I make a formula? Why don't I make a function? Why don't I make a function in Haskell that actually does this? That actually does this piece of the computation. Okay, so in order to get this ai plus 1, let's call the function next. I mean, I'm trying to get the next value, right? All I'm trying to do is get the next value. So let's create a function called a next. Okay, now what does next require as an input? Well, it requires as an input a couple of things. the first thing it requires is this n, right? It requires what's the number that you're trying to find the square root of. So let's pass that n there, okay? And what does this require? Well, it requires the initial a that you have. So given this ai, and given this n, all I need to do is just plug in these values into this equation on the right hand side, and I get back the next value. So I'm going to say n of ai, and then I'm just going to plug in the entire formula there. Okay, and that's the function. That's what my function is doing. It's a function that takes in two parameters. Okay, it takes in two parameters and gives you back that value there. Okay, so why don't we create that in Haskell first? Why don't we just create a function called next that simply gives you the next approximation? Okay, so let's do that. So let's start up our Haskell shell, and I'm going to say let next of n of a equals to the old value a that I had plus n divided by a. I'm just plugging in the formula there. This entire thing, then divided by 2. Okay, so this is with some parentheses there just to make things a little clear, and that's pretty much. I mean, it's pretty straightforward. That's all this function is doing. Let's get a type signature for next here. Okay, so what does next do here? So next basically is a function. It's a function. I can see that's kind of a function right there. It's a function that takes in some kind of a number a. Okay, takes in basically some value of type a. It takes in another value of type a, and then it gives you back some value that also belongs to the same type a there. Okay, and this piece over here, the first piece that goes into the function is basically this n there. The second piece that goes into this into this function happens to be this second argument, which happens to be this piece over there. So remember, this a over here is just a variable there. This a is nothing to do with the a that you see in this type signature. Okay, this a has a constraint. The constraint here is that it must be a fractional number, a number that has some kind of a fractional component, and that's the only constraint that is associated with this type variable. Okay, and finally, after consuming this input 1 and consuming this input 2, what you get back is this output here, which is this piece there, which is this entire piece. Okay, and if you were to use I don't know, functional coloring, you could rewrite this as if I just rewrite my type signature there. Okay, it's nothing but if it takes in one, every Haskell function takes in one input. That's what it does here. It takes in one input, but in return it gives you back as an output some kind of a value that happens to be a function. Okay, so you can think of this piece over here, the first piece over here, as your input. Okay, using the Haskell's coloring style notation there, and what you get back over here is some kind of an output. Okay, so this is pretty simple, pretty clean. I mean, and that's pretty much what I need to do so far. I just have some function that's going to help me to get the next approximation. But now what I really need to do is, if you read the question again, what I really want over here is basically a list of all these approximations. Meaning, what I want really is a list over here that contains a0, a1, a2, a3, up to an. At some point be an plus 1, an plus 2, and this goes on. This goes on. It goes on for infinity. Okay, so give me back a list over here, and the idea is at some point these values over here will get very close to each other, meaning they're going to be completely equal to each other, meaning the difference over here between an plus 1 and an should start approaching 0. Okay, so that's the kind of the idea there. So give me back a list here. Give me back a list where that has all these approximations listed. Okay, so how do I calculate the first approximation? Well, the first approximation you don't calculate. It's already given to you. I'm giving you the initial approximation that I have, that may be the square root of n. So this is already given to you. The first piece is already given to you. This is kind of the piece that's already given to you. Okay. Okay. So that green box is kind of given to you. Okay. Given the a0, how do I get a1? Well, to get a1, all you need to do is just apply that formula. I mean, I don't want to use the word formula here because I'm not in. I'm kind of right now in the Haskell world here. But I'm saying I need to just apply that function there. Okay, so that's the deal. Apply that function, and how do you apply that function? Okay, so what does the function do here? It says next n of a. So what was the previous a? Remember this a over here. This a over here is the kind of the previous a that I had. Okay, the previous solution that I had, the previous approximation that I had here, and then this entire piece in blue Let me just use a slightly different color here. Let me use white. This entire piece, white isn't good. Uh, let's see, don't have too many colors here. Let's use red. Okay, so this entire piece over here in red now. This entire piece in red, which is next of NA. Next of NA is your entire next approximation. Okay, so this piece A1, in order to get A1, I simply going to plug in that going to plug in that function, and I'm going to get back away. I'm just going to say next of n. Okay, that's my n there, and A0. Okay, that's what A1 is. This is what A1 is. This entire piece is what A1 is. Okay, how do I get A2 then? Okay, if this entire piece is A1, okay, so let me just kind of, I don't have space there, but I'm just going to write a little bit over here on the some space that I have on my just after this. I'm going to say that entire piece next of n of A0. If this entire piece over here is A1, on that A1, reapply the function which is next of n. Remember, what does next do? Next takes in the number n, which is the number that you want to find the square root of, and it takes in the previous value, the previous approximation that you had there. The previous approximation that I have now is this box here. So this entire piece in green now, this entire piece in green, is now A2. Okay, so this piece over here, again, I don't have too many colors here. I'm kind of reusing my colors here, which I don't like. So let's just put this piece in orange. This piece in orange is your A0. Then this piece in red over here is your entire A1. And this piece over here in green is your A2. Okay, let's just find out what A3 is. Okay, so if this entire piece in green, let's just rewrite that again. So I'm going to say next of n of next of n of A0. Okay, so this piece, and then again on this entire piece, if this entire piece over here is my A2, then on that entire piece, if I call next n again, what I get back is this A3. This entire piece now becomes A3. This piece becomes A3, and so forth. If you keep on doing this over and over again, what you get back are these different and different approximations. Okay, so can I simplify this a little bit more? Can I make this a little bit more clean here? So let's kind of revisit that list again. Let's revisit that list here. And let's just rewrite my A0, A1, A2, A3, and it just goes on. Okay, A0 is given to you, so let's just kind of rewrite that as A0. Okay, it's already given to you. What is A1 here? So what I'm going to do is whatever this next of n is, I'm just going to say let's have function f. Let's have function f. That's just simply equal to next of n. Okay. Now, is next of n a function? Yeah, it is a function. I mean, this entire piece here is the type signature. For next. Okay, but if next takes in one argument, what it gives back to you is this new function, which is a function also, right? And that's what this f is. This f over here is this function that gets returned back to you when next consumes a parameter. Okay, so I'm going to say, instead of keep on writing this next and I'm just going to rewrite now as f of A0. Just the same idea. I'm just kind of just substituting wherever I see next n with f. This piece becomes over here f of A0. Alright, this piece over here becomes f of A0. Okay, and so forth. Okay, this is good. I'm making a little bit of progress here. Now all I need to do is write a function that gives you back this kind of a list. It gives you back a list where you have all of these approximations, and that's what the problem is asking you. It's just telling you, give me back a list of all these different approximations. Okay, so how do I generate this list here? Now Haskell already has an inbuilt repeat method that you can actually use, but let's just take a little bit of trouble here. Let's just spend a little bit of time to reconstruct the repeat ourselves. Okay, so how would I construct a repeat function? Now what does repeat require? Okay, so let's kind of see how am I going to put a function called repeat over here. So what does repeat do? What's the type signature? What's the type signature for repeat? Okay, so repeat says, or the function says, or the repeat function says, okay, give me give me some initial value. Give me some initial value a0. Okay, so let's just give it some value of type a. Okay, given some value of type a. Okay, and give me a function. Give me this function because this function f just keeps on getting applied. So I definitely this needs to be taken in. Okay, so it takes in maybe as the first parameter this initial value a, and the second parameter is this function. That function may be, I don't know, could be going from some a to b, and because of function there, I'm putting those things in parentheses. Okay. All right, so that's my first argument, which is some initial approximation. Then my second argument is this function f, and what does it give you back? It gives you back, some kind of a list. It gives you back some kind of a list where this f has been applied over and over again. So it gives you back some kind of a list of type b. Okay, so let's kind of think about this. I mean, let's just writing this a very kind of a generic notation there. But I kind of want some kind of a function repeat that basically has this following type signature. Okay, and if I can somehow put this thing together here, what I'm going to get back is this entire list generated there. Okay, so now if just to be a little bit clear here, this function over here, I mean, let's not put b there because b could mean a different type as well. And what I really want is this list of all these a's again, right? So I have a function that basically goes from an a to a. That makes it a little bit more clean there, and a little bit more something that makes me a little bit more uh, comfortable with. So what I have here is this repeat that takes in some type of a. It takes in a function. It also goes from an a to a. Okay, because if it were to give you back a b, some different type b there, okay, then what I really have here is a list that happens to be heterogeneous, and it also doesn't satisfy the type constraint associated with that function f, because if f of a gives you back some type, if this gives you back some type that happens to be of type b, then f now is consuming this type b, which could be something different than a, right? So f always takes in some input. Remember this entire thing over here, is a type signature for f. Okay, f is a function that always consumes in some type of a there. So when this f, the second f over here, works on, it should still be consuming something of type a there. It cannot consume something of type b. And eventually what you get back is this list over here that should still be a homogeneous list, meaning it contains every value that happens to be of the same type. So that seems a little bit more clean and a little bit more something that I can live with. So let's try to get this function repeat put together. So coming back over here, I'm going to say let my repeat, and I'm just going to call repeat prime there, which basically takes in let's say it takes in some a. Okay, it takes in the function f, and what it does is basically it regenerates this kind of this list there. And the way I'm going to generate that list over here is I'm going to say the first item that gets generated in this list. So if you look at the first item here, the first item in this list was basically a0. That's the first item. Okay, so how am I going to generate a list with the first item a present? Well, just put a there, use a cons operator, and then what I want to put over here in this placeholder is basically this new list, right? So what's the type signature for the cons operator? The cons operator, okay, the type signature for the cons operator is basically it takes in some value of type a, it takes in a list of a's and gives you back a list of a. That's how the cons operator works. Okay, so it basically takes in this value and just puts in at the very first position in this list there. So here I'm using this as an infix notation. So this a over here that I have is basically this piece there. Okay, and whatever's in this box here should be some value of this type, of this entire type list there. So how do I get that list there? How do I get this new list there? I'm just going to use recursion. So I'm going to say, okay, look, I already have a function. That gives me that list. That function is right here. Okay, so I'm going to call this using recursion. I'm going to put everything in that box there. Okay, so I'm going to say a cons, and I'm going to say repeat, and again a, and this now takes in f of a. Okay, so this new list that I want back. Okay, so let's just look at the new list here. Okay, so a0 has already been put into my list. Now this new list that gets, so let's do this. Let's kind of rewrite this. Let's rewrite this list here. Let me kind of rewrite that list here in something that's easy to understand, which is f of a0, f of a0. 0, f, f, f of a0, and so forth. Okay, I'm just rewriting that list using the cons operator. Okay, so a0 has already been inserted as I'm creating my repeat function. Now what I want back after the cons operator is this new list here, which happens to have the first item. The first item is f of a0. Okay, and that's what I've done here in my code. I'm saying f of a0, the initial value. Okay, so let's press enter. All right, so what I have now is this piece there which says repeat takes in that a, it takes in that f, and I'm calling this over recursion using recursion again. So I'm saying in this is my initial value a. I'm calling the repeat function again, which takes in as the new initial value, which is f of a there, and it takes in that function f over there. Okay, so now let's just apply the square root. Let's just call the square root on my so let's just have something called let me get this list of approximations, and I'm going to call my repeat function the initial value a. Let's say the initial value for the square root of 9. I'm just going to put some value there which happens to be 2, and I'm going to pass in the function f. I've already created my function f, which is this piece over here. So this my function next that already has been created. So I'm going to say next of n. Okay, so remember this function f is a function f that just consumes a value of this type a there. Okay, so it just consumes one parameter. So I'm going to say next of n directly. So this function that you see passed in, this f over there, I'm going to say this f is going to be next of, let's say, I want to find the square root of 9 there, so let's say next of 9. Okay, and if I run this, I get back a list. That happens to be a list of all these approximations. Okay, let's just see the first value in this list here. If I see the first value in this list over here, as expected, I see that the initial a0 in this list over here is basically 2. Okay, so going back to my picture here, which is right there, this a0 initially is actually 2. Okay, what's the second item in this list? The second item is going to be a1, and this a1 is going to be f of a0. Okay, going to apply this function f, which f technically is this next of n. Okay, next of n. So let's try that. Let's see what's the next item in the list there. The next item list is 3.25. Now you can see I'm getting a little bit closer. To that true value. So let's just try one more iteration with the next index value. That gives me 3.009. And if I go once more, I get something more, a little bit more closer, and so forth. Let's just get the entire list. Let's get the first 10 items in the entire list. So I have a function in Haskell called take. And what take does is says, okay, it just returns back to you a subset of this list. So it tells you how many items should I take from that list there. So I'm going to say take the first 10 items. And what list am I talking about here? The list is approx, and it's going to give you back a new list, right? It basically gives back a new list with just 10 items in. So I can see this, if I look at this list here, I can see that the values are 2.0, 3.25, and as I keep on moving towards the right, I converge to the true value, which is in this case happens to be 3.0. Okay, and likewise you can try this again. Let's just try this again with a slightly different value. So let's say I want to find the square root of 16, and I'm going to assume that let's say the initial approximation happens to be 7, and if I get the first 10 approximations there, I can see that starting with 7, it starts to converge. Towards the value towards 4 there. So 4 in this case happens to be the square root, the one of the square roots for the number 16.